All right. So, anybody have any questions from last time? What have we talked about so far?
Strain tensors?
Yes, that's what we're talking about right now is strain. We talked about the stress tensors before then. So we're going to finish talking about strain. What type have we talked about so far? Don't look at notes. That ruins it. What? Yep, we've talked about normal strain. So I'm going to give one example problem. And then we're going to talk about shear strain. And what do you think we're going to talk about after strain? We've talked about stress, talked about strain. Now what? Dancing? No. So then the next topic is the relationship between those two, which is like going to be the matrix version of the spring constant, okay? So you have that to look forward to. But right now we're talking about strain. Here's an example. So say that you have a material that before deformation has a height of 0.008 meters and a width of 0.01 meters. And let's say that we're using a coordinate system with the y-axis this way, the z-axis this way. So which way does the x-axis have to point? So the x-axis would have to be coming straight out at us because x cross y, right-hand rule has to give z. Yep. Okay, and after the deformation, I'm sort of exaggerating this deformation so you can kind of tell what's going on, but it deforms into something with a height of 0.011 meters and a width of 0.005 meters. And let's say that the thickness for both is 0.015 meters in both states. What are the normal strains? Okay, so the definition of the strains, the x normal strain, epsilon xx, is equal to the new length of the x edge, x side, minus the initial length, divided by what? Divided by the initial, yep, that's right. And so what is the final length of the along the x-axis? Yeah, that's right. So the x direction is the one where the length doesn't change, right? The x-axis is pointing out of the page, and so if you take that measurement along that axis into and out of the page, that's where you have 0.015 meters before and after, okay? So we have 0.015 minus 0.015 divided by 0.015, so you get 0. And now the y normal strain, so that's going to be the length after the deformation minus the initial divided by the initial. What's the length along the y-axis after the deformation? Yep, 0.011. And before the deformation, yep, 0.008. Divide by what? Yep, good. And so you get a value of positive 0.375. What are the units on strain? So strain is dimensionless because you have a length on top dividing by a length. So this is the strain no matter what units you're using. And what does it mean that it's positive? That is stretching. Yep. If you get a negative answer, it means it's right. And now the Z. So we have LZ minus L0 over L0. So what is the final Z length? Yep, 0.005. Before the deformation, 0.01. Divide by the length before the deformation. And you get negative 0.5. So if you are going to put this in the Voigt strain, there are no shear strains. How do I know there's no shear strains? We haven't talked about how to calculate those yet. But remember, shear strains represent angle changes. And so if something starts out with all the angles at 90 degrees, like a rectangular solid, and finishes with everything at 90 degrees, then the shear strains are all going to be equal to 0. So the Voigt strain is equal to 0.375, negative 0.5, and then 0, 0, 0. Sorry, that's so small. Okay. Notice in this example, these are bigger strains than we'll ever deal with in real applications. So than we'll ever see in realistic problems. Remember that we need to have small strains in order for our approach to even work. So small strains is one of our modeling assumptions. So the real strains that we'll deal with are going to be around 1 times 10 to the minus 4 or smaller. Okay, so now shear strains. Shear strains are changes in angle between the faces. And so if you start out with an element that looks like this, say it's rectangular, so all of these are right angles in this coordinate system. then after deformation, say you have something like this, okay, we're going to define this angle theta xy as the angle between the positive x face and the positive y face. So notice if you didn't use the positive for both of them, like you could end up, if you used, like, say, the negative x face and the positive y face, you'd have an obtuse angle when what we want in this example is the acute one, okay? So you need to, it needs to be between the correct two faces. But if you define all the angles like that, then the xy shear strain is equal to pi over 2 minus theta xy. The xz shear strain is equal to pi over 2 minus theta xz. And the yz shear strain is pi over 2 minus theta yz. So for all of those angles, let's say theta AB is the angle after deformation between the positive A face and the positive B face. Okay, so in the sign convention of normal strains, we know that a positive normal strain means that the object is elongated along that axis. Negative means that it's compressed along that axis. What does the sign convention here mean? So what it really, since you can think of this pi over 2 that we're subtracting everything from, means that 90 degrees, a 90-degree angle is like the default. So everything is like, the question is it bigger or less than 90 degrees after the deformation? And so to get a positive value, that angle would become acute. To be a negative shear strain, that angle would have to become obtuse. Okay. Yes, thank you. I'm glad you mentioned that. So yeah, all angles are in radians. Okay, so notice if the angle gets more acute, then you get a positive shear strain. If the angle gets more obtuse, you get a negative shear strain. Okay, so here's an example. So let's say that we're going from a rectangular shape in this coordinate system. No, let's make this the z-axis. And after the deformation, it looks like this. where this angle is 1.43 radians. And in all other views, the angles remain at pi over 2. Okay, so if you looked at it from the side, everything would still look like right angles. But in this one view, you can see that the angles changed. Okay. What? Not the back. Okay. So what are the shear strains? Okay, so what is the angle that matters to us? Remember, that's a key thing. If we calculate this based on the wrong two faces in this view, we'll get the wrong answer. So we have to figure out what the positive x and the positive z face are, and that's the angle that we want. Okay, so the angle that we really want is this one. Okay. Do you see that? No? So the positive x face is this one. The positive z face is this one, because those are just like, those are the faces in the direction of the positive axes. And so this is the angle that we want between the positive z face and the positive x face. In this one, you mean?
On your coordinate system.
Uh-huh.
So why is the vertical line then the z-axis, like the z face?
So remember, you think of it this way: take the coordinate system and put it right into the middle of the element, and then the positive axis points at the face with that name. You know, so like if you move the coordinate system to here, then the z-axis is pointing at the z face, the x-axis is pointing at the x face. Okay. You could also think of it as the face is the one where the positive axis points directly out of the face, you know? So I think it's easier to think of it as just put the coordinate system in the middle. And if you look back at the stress cubes that I defined when we're talking about stress, this definition of the x face, the y face, makes sense with the definition we use with the stresses too. Okay, so what's this angle? Well, we know that these two together have to add up to pi. So pi is equal to 1.43 plus the angle that we want. And so theta xz is equal to 1.71 radians. Any questions about what I did there? And so then to calculate the shear strain, shear xz is equal to pi over 2 minus 1.71. And so you get about negative 0.1392. Now in the other view, if you looked at the view where you could see the x and y axes, those all remain right triangles. So you have stress xy is equal to pi over 2 minus, so theta xy would also be pi over 2. And you get 0 shear strain, which is what you would expect if there's no change in angle in that plane. And then the same thing with the YZ face, pi over 2 minus pi over 2, so 0 strain.
Where did the 1.71 come from?
That is pi over 2, that's pi minus 1.43. So these two angles are complementary. That's what that's called, right? They add up to 180. So so 180, pi has to equal this one plus the one we're trying to find, and then just solve that.
Do you get a normal, when you kind of collapse the square into a parallelogram, the height changes at that?
No, not necessarily. So,
Okay, so you measure the height at an angle then?
yes. So yeah, I think I have an example here. Well, let's do an example like that so you see how it all works. So let's say that you start out with this, and all these are right angles. And after deformation, you get, well, let's say that this is 1.3 radians. Let's say that this is 0.15 meters, and let's say that this is 0.007 meters. Okay. All right, so first let's do the calculation, and then I'll talk about what I think your sort of, the question that at least what you were asking brings up. So let's say everything else stays unchanged. So so what changes? Well, the normal strain in the x direction changes. The normal strain in the y direction, is also non-zero. And then the xy shear strain is non-zero. Everything else will be 0. Okay? So let's calculate those. So the x normal strain, it ends up as 0.007. It started out at 0.01. Started out at 0.01. Can someone divide that? I don't have these calculated. What is it? Okay, negative 0.3. And again, that's too big a strain for our purposes, but it shows, how to do this. And then EYY is that was supposed to be 0.015. Yeah, that would be way too big. Okay, so 0.015 minus 0.01 divided by 0.01, positive 0.5. Oh, I could have done these in my head. And then This one doesn't change, so that's 0. And now we go to the shear strains. Shear xy is equal to pi over 2 minus. So is this the angle that we want, or do we need a different angle? This is the one we want because the positive x face is this one. The positive y face is this one. And so they meet at this angle. So that's the one we want. So pi over 2 minus 1.3. What do you get for that?
271.
Okay. And then shear xz is equal to shear yz is equal to 0. And so the state of shear written as, or the state of strain, I mean, written as the Voigt strain is equal to negative 0.3, positive 0.5, 0. And then what comes next in the Voigt form? The YZ comes next. Remember, now the shears go in like the least sensible order you can imagine. So we got 0, next is XZ, and finally is XY, 0.271. Okay. So what's the deal with this? This isn't really the length of that side anymore. It isn't the length of that edge, right? We'd have to do trigonometry to figure out the length of that edge. So I just sort of glossed over something here. So what's the deal with that? That's my question. What's the deal with that?
Projection on the slide.
So that is how we do it, is like as a projection, but like, why would we even think that that might be okay, you know? Well, the answer is we're assuming small strains, and small strains means small shear strains too. And if you have small angles, I didn't draw it as a small angle, but if you have small angles, that difference between the true length of that edge and just that height measurement along the original axis vanishes, you know, it's negligible. And really that difference between how you calculate the lengths before and after the deformation is maybe the most important reason that we're assuming small strains, that we're not dealing with big strains. Okay, like you can do that stuff, but it makes everything horribly complicated.
Could you just say that times the tangent of the string?
This times,
Side of the string
so
to get the length.
I guess it would be the, like you divide by the sign or something, right? But yeah, but whatever, like, yes, you could do that, but we're not gonna do that. And the reason that we think it's okay to do that, the reason that it makes any sense to do that is that these angles are small. So when you really looked at what this deformation would look like, one would look like this, and one would look like this, you know? The difference in those angles is very small, and so the difference in the height versus the true length of that edge is very small. So you wouldn't have thought of that if you were watching this at triple speed. Any questions about that? Okay. So now I've mentioned Voigt notation for strains. But you can also write the stresses in Voigt notation. So the Voigt stress looks like this. The three normal stresses, followed by the three shear stresses in that funny order, YZ, XZ, XY. Okay? And our constant of proportionality between the stress and strain will be a matrix where, and let's see, what's the form that we usually use? So usually we're going to have the strain equal to a matrix times the stress. Okay, so what kind of matrix does that have to be? What's the size of that matrix? Each of those vectors has 6 elements. Yep, so this has to be a 6 by 6 compliance matrix, it's called. And it's called the compliance matrix because the elements of this matrix are bigger if the material is more compliant. Okay, so whatever the stresses are, if these values are bigger, you get bigger strains out of it. Those stresses made the thing deform more. If these values are smaller, then it means the material's stiffer. So bigger values mean the material is easier to deform. You could also, so let me say less often, we'll use the calculation where the stresses are equal to a matrix times the strains. Whoops. Okay, so this is a different matrix. This is also 6 by 6, but this is called the stiffness matrix. And in this case, bigger values mean the material is harder to deform. And the relationship between, question?
Yeah, stiffness matrix and compliant matrix, is there any difference between two or just?
They're different. Yeah, they're different, but they're very closely related. They have to have all the same information in them, but they're different matrices. And the relationship is this. The compliance matrix, the stiffness matrix is equal to the inverse of the compliance matrix. And you can, if you've done anything with inverse matrices, you can see how that works. If you haven't, it's not really a big deal, but your calculator does inverses for you. But so now we need to talk about how to calculate the elements of those matrices, usually the compliance matrix. I want to say one thing about this too. So regarding the, let's say, the relationship between stress and strain. The word elastic, so what does elastic mean? Okay, so yeah, it means that. And I think like a lot of people, like it probably came up in physics at some point. Well, you do collisions, like elastic collisions. So what is it that makes fruit of the loom elastic waistband elastic, you know? Like it stretches, and that's how I always thought about it too until I started taking physics and stuff. But it's actually not the stretching, like it's that it springs back. So what elastic is when you unload something, it returns immediately without any lag time to its initial configuration. You know, its reference, whatever. And so we're dealing with, in this class, elastic materials. And what that means is that the shape of the object is entirely determined by the loading. If you take the loading away, then without any lag time, you assume that the material is instantly back at its reference position. Okay? So think about that for a second. So what would happen if you... So okay, so the fact that you could come up with any relationship just entirely between the stress and the strain, okay, no matter what the relationship is. It could be a differential equation, whatever, some complicated thing. But if there's a relationship between the stress and the strain, that means that the material is elastic, okay? Because the shape of the object is entirely determined by the loading. If you take the loading off, the material is back at its reference configuration, okay? We have something else going on in this class. So let me try to write that in a simple way. So the fact that, let's say, strain is entirely determined by stress, or vice versa. But the fact that you don't have to put anything else into the calculation to calculate one means the material is elastic. We have something stronger here. And that is that for us, the material is elastic and the relationship between stress and strain is linear. And what do you call that? Well, this makes sense, linear elastic. So it's a linear elastic. We're dealing with linear elastic materials. So as you're just sort of trying to sort through these terms, like when you see when you get a problem that isn't connected to a class, someone asks you something about how this brick is going to behave or whatever, there are a couple different questions you have to ask yourself. Is there a reason to believe that it'll behave elastically? Some materials, that's not a good assumption, Play-Doh, you can't, it's not just the fact that there's not a linear relationship between stress and strain. If you take the load off Play-Doh, it stays where you put it, or water, gel pudding, whatever. Those aren't elastic because you deform them, move your hand, they stayed where you put them, okay? And then once you know that you have something that can be treated reasonably well as elastic, then the next question is the relationship between stress and strain linear? If you have both of those two things and the other modeling assumptions, that we've talked about, then the techniques in this class are applicable, okay? Okay, let's stop there and we'll do constitutive relationship next time. So the constitutive relationship is like fancy wording for that constant of proportionality, or what is the relationship between stress and strain.